I'm Jeff, and as he said, I'm going to be talking about glacier flow. I'm working with Tom and Teufel over at CU Boulder, and Hari Rajam. So let's just get right into it. Today I'm going to talk about general Stokes for glaciers, then specifically this new formulation that we're coming up with, which we call the fluidity form. I'm going to talk how we solve this system. Then I'm going to describe a very simple two-dimensional model, and then show some numerical results. So first, Stokes. So we're going to assume we have an incompressible system. Basically, ice can't be really compressed very well. So we have our continuity equation is just divergence of u equals 0. And then the momentum equation consists of our local acceleration, our vective acceleration, our stress divergence, and then a forcing function. We're going to try to solve for a steady state solution so we can get rid of the local acceleration. We're going to assume the vective acceleration is small, so we'll get rid of that, which leaves all we have left is the stress divergence and the forcing term. So our current goal is to rewrite stress divergence in terms of our velocity vector, u. This can be done by first decomposing stress divergence into the deviatoric and the hydrostatic stress. Hydrostatic is basically how things expand and compress, and deviatoric is all of the other deformations. Since we're an incompressible fluid, the hydrostatic portion is just negative P, or pressure. And then the deviatoric becomes the expression 2 times the viscosity times the strain rate. The strain rate can be written as the symmetric gradient of u, where in this case the gradient of u is a matrix where the columns are the gradient of the components of u. And then viscosity we derive from Glen's flow law, which is this nasty. How do I make the middle button? There we go. Which is this nasty thing. Our A term here is dependent on temperature, but for all of our simulations after this point, we're just going to assume it's constant, so we'll get rid of the dependence on T. And then N we set to equal 3, which gives us this law. One of the problems is that this epsilon E will go to 0, which will make our viscosity go to infinity, which I'll talk about later. But the reason we use Glen's law in the first place is, well, it's empirically derived from a stress-strain relationship, and it's what everyone else uses. So I kind of have to be stuck with this pretty horrible law. And we're going to try to find a way to make it better. But before we get to that, let's just talk about Stokes again. So here's the full system. We have our continuity the same, our momentum now with our viscosity and our symmetric gradient, and then there's our definition for viscosity. Since we're going to try to use FOSLS on this system, we want to first convert into a first order form, which we do by making this new definition, capital U equals the gradient of u, defined as such. Then when we plug it into our system, we get continuity, remains the same. We get our new definition, big U equals gradient of little u. And then our momentum equation, just we replace the gradients with the big U's. If we take the curl of the definition term, we get that the curl of big U equals 0, because the curl of the gradient is 0. And then lastly, we enforce that the trace of big U equals 0, and this comes from just the continuity equation. And in our two-dimensional case, this is enforced strictly by just setting U11 equal to U22. And this right here is the viscosity formulation. The reason we add these two equations is to enhance the norm with which we use to approximate our solution. So now let's talk about this fluidity form. As I said before, there's a problem with viscosity in that when this term goes to 0, viscosity goes to infinity. Well, this term is dependent on the gradient of u, which is basically saying viscosity goes to infinity when the ice is acting like a solid, which makes sense. So to try to combat that, we're going to absorb that term into our big U term. Now this term goes to infinity at about the same rate that this term goes to 0. So the combination of those two behaves kind of like a cube root, which is a lot nicer than blowing up to infinity. So we make a couple more definitions, and we get this phi term, which we can express in either the new set of variables or the old set of variables. If you notice, when we express phi in the old set, you get basically that problematic part of viscosity, the reciprocal of it. And in physics, the reciprocal of viscosity is called fluidity, which is why we named this the fluidity form. Okay, one last little change we make is to scale out all those constants. And then if we multiply this scaling by, multiply the momentum equation by the scaling, we get this nice system. Well, almost nice system. There's one more little problem that we have to do, and that's fix the balance between the curl equation and the gradient. The divergence. We do that by basically scaling the curl by 1 over fluidity plus c. This way now the divergence in the curl will be better scaled, which will help AMG in the long run. We can take the product rule of this to get a grad perp form, which in tests has performed better by just reducing the number of nonlinear iterations that we have to perform. And we believe that's probably because this is close to being an unscaled curl equation and then some lower order terms. Okay, so let's talk about the numerical methods. We have a nonlinear system, and we want to linearize it. So what we do is we let this fancy L denote our fluidity formulation, and fancy U denote the collection of variables that we're solving for. Then we take our Fauché derivatives, drop out the higher order terms, and we get this nice Gauss-Newton iteration. For notation's sake, we're just going to let the new linearized operator be denoted as blackboard L, and the right-hand side be denoted as R. Now we want to solve this new linearized iteration, and to do that, we're going to solve it using a least squares method, which basically amounts to minimizing this norm, which we can show is equivalent to solving the weak form, that guy. If we actually analyze the fluidity form, if we consider this linearized functional, we can say that if we have enough regularity in our previous guess, that our fluidity form is continuous. Coercivity, on the other hand, is a lot more difficult to prove. There have been papers about coercivity for Stokes with constant viscosity and durationally boundary conditions around the entire domain. But for the case of variable viscosity with more general boundary conditions, this question is still open, and it's something I'm working on. The solver that we actually use is called FOSPAC, and how it works is we do our Newton iterations, we discretize the linearized PDE, and then we solve using preconditioned CG, which is preconditioned with AMG. Then after we've iterated enough to be satisfied with the result, we refine the grid and interpolate up. Now, I've shown here uniform interpolation, but we can very easily just use an adaptive mesh refinement. So let's talk about that 2D model, the very, very simple 2D model. Here's a list of parameters if you ever want to reproduce this. But our model is basically a big slab of ice flowing down a hill at a constant angle. Now, the slab of ice is infinitely long, and the hill is infinitely long, which will give us a lot of cool properties. To make our lives even easier, we simply just rotate the computational domain, and now we're solving on a rectangle, and everyone likes to solve on rectangles. So the boundary conditions. On the top, we want to impose a stress-free boundary condition, which is basically that sigma dot n equals 0. Sigma in this case is the viscosity times the symmetric gradient minus p. If we pull in that problematic part of viscosity, we get our u hats. If we then scale by b, we get this term, which I've denoted sigma hat. And notice that sigma dot n equals 0 implies that sigma hat dot n equals 0. So the stress-free boundary condition on the top can be expressed as these two conditions here. Keeping in mind that we're strictly enforcing u11 equals negative u22, and we get the actual conditions that we impose. On the bottom, it's a little bit easier. We have a no-slip condition, which is basically that the velocity vector equals 0, which says also if we take the directional derivative along the bottom, we would have that those derivatives should also equal 0. So we get our set of boundary conditions for the bottom. And then finally, as I said before, we're using an infinitely long glacier, so we just kind of assume periodic boundary conditions on the side. With all of these assumptions and the nice periodicity of our domain, it's easy to see that the velocity vector will be only one component, and it will only depend on z. We can then backtrack what the actual solution is, and there it is, which will be very helpful in calculating error later on. If we graph the velocity profile U1 with respect to height, we can see that in this region, the glacier is moving at pretty much a constant speed, which corresponds to a pretty large viscosity, going off to infinity exactly at the height. And yeah, we're like in the millions by just slightly above 800 meters. So this test problem exhibits the issue that we were talking about earlier with the infinite viscosity blowup, which will make it an interesting case. So let's talk about the numerical results. The first graph I'm going to show you here is the functional convergence. Basically, we're using linear elements, so we would expect the functional to be reduced with order h as we increase the number of elements. And as you can see, both the fluidity and the viscosity form do just that. So this tells us that our solver is doing what we expect it to do. Looking at the L2 convergence, we would expect, again, for linear elements, we would expect order h convergence. And for both the viscosity and the fluidity form, we get our order h squared convergence. Nice thing to notice is that the fluidity is 14 times smaller than the viscosity. Now there's a bit of a caveat there. In order to even actually solve the viscosity form, we had to add a small constant into the effective strain rate, which will increase the regularization of viscosity, but will decrease the accuracy of the solution. So if we were to make that small constant even smaller, we would get more accurate, but the performance of the solver would just go to heck. It'd just be terrible. So this specific one was chosen for a combination of performance and accuracy. Last thing to look at is AMG performance. So this is a graph of the convergence factor for the preconditioned AMG system. And what we see is that the fluidity form has a maximum of 0.58, and the viscosity form has a maximum of 0.98, where these numbers basically is how much the FOSLS functional is reduced with each iteration. And that means that in order to get the same level of reduction as the fluidity form, the viscosity form has to perform about 27 times as many iterations. So fluidity form is winning again. Now if we look just at the fluidity form, I've made a work units table to show how much it costs to actually solve the system. Here work units are equal to one work unit is equal to a matrix vector multiply on the finest grid. So these are fine grid equivalent work units. And we can see that the whole solve takes about 40 work units, which is equivalent to about 40 Jacobi sweeps, which is pretty nice. Another test we did is starting with a random initial guess and looking at how many number of Newton iterations it takes to meet some sort of a criteria. And as you can see, it takes a lot of Newton iterations on the finest grid. On the coarsest grid, very important, coarsest grid. And then it takes a couple more on the second coarsest grid, and then about the time we get to the third coarsest grid, we're just taking 1 Newton iteration every time. This is one of the fantastic qualities of nested iteration, is that all of the iterations are done on the coarsest grid, and solving on the coarsest grid is really cheap. So by the time we get to the finest grid, we only have to do 1 Newton iteration. Last thing I wanted to talk about in terms of performance is mass conservation. We're doing Stokes in a FOSLS framework, and what always comes up is people ask, are you conserving mass? So what I did is I did cross sections along the 100 to 2,500 and so on parts of the glacier, and I calculated the integral of velocity dot n. Well, that just becomes the integral from 0 to 1,000 of u1 dy, where this I refers to, are we doing it at this point, 5,000, 7,500, or 10,000. And then what we want to actually calculate is the difference between basically how much mass loss we have at each of these 3 blue points. It's kind of interesting to note that because we have the periodic boundary conditions, we know that this line and this line should be equal. So this is one way to look at it. This is the mass conservation on each one of those slices for all of the levels. Unfortunately, the first level completely dominates, but at the same time, we're still at 10 to the negative 8. So we're conserving our mass pretty well. If we get rid of that first level, we can see that the other levels are kind of all in the same area. But there's a general trend going down, where this is the 6th level, and this is the 2nd level. If we look at it a slightly different way, we can see that here are the nested iteration levels, and here are the slices that we're looking at. And basically, after our first nested iteration level, we just kind of oscillate around somewhere below 10 to the negative 10, which is pretty good for mass conservation. That's like 10 digits of accuracy for each one of the slices that I showed. Last thing I'm going to talk about is adaptive refinement. As we saw before, we got pretty much not uniform, we got pretty much optimal convergence in the L2 sense and in the FOSLS functional sense. So we don't expect adaptive refinement to give us much, but it's still interesting to look at. Our adaptive refinement method is called ACE, which basically looks at how much it would cost to refine a certain element, and then weights that with how much accuracy you would get. So it gives you an accuracy per computational cost estimate, and then refines accordingly. As you can see, we basically have the same order of reduction, but we use only half as many elements to get to the same level of reduction. And the reason for that is our system is pretty periodic. It's pretty uniform in general, so we wouldn't expect to get much of a speed up here. And if you look at A, which is our initial state, B, which is the uniform refinement state, and C, which is the ACE refinement state, we get that C is pretty much the uniform grid on about half the domain. So that's about what we would expect. Okay, so conclusions. I've shown that glaciers are modeled by Stokes. I've shown that the viscosity becomes infinite, which is a problem. And I've discussed a way of fixing that problem using this fluidity formulation. My future work is to get these ISMIP benchmark problems, which are basically a set of 6 different test problems that all glacier models tend to compare against to see whether or not they're getting accurate solutions. And I'm really close on doing that, so hopefully we'll get that in the next couple of weeks. We want to include a thermal model, and then the thing that I really want to do, because I like to show movies and I haven't gotten to show a movie yet, is time-dependent domains. Basically, we solve for the velocity field, use the velocity field to update the domain, and then repeat this process until tens of thousands of years, because that's how long these things take. And then I can show a really cool movie. But you'll have to wait for that one. Anyways, I want to say thanks to everyone at the Grandview and my advisors, Tom and Hari, and of course Steve, wherever that tie-wearing guy is. And then of course the people who gave us money. So thank you.